Again, welcome to this class. This is the written assignment that was given on the 2nd of July 2024. The assignment read, consider the statically indeterminate continuous beam subjected to a distributed load. Solve the structure by means of the two standard coefficients at the back of the page. I will then draw them on the blackboard. Determine the restraint forces at the four supports. A is a hinge, B, C, and D, I will now mark the letters, are rollers. Plot the diagrams of the internal forces, clearly indicate the sign conventions. Calculate the rotation at the second support, point B, clearly indicating its value as a function of P, L, and E, J, and sign clockwise or counterclockwise. This is the first part which deals with the structural analysis of the structure. So I will start off with this and then we'll go through the other points which deal with the design of the different sections. Okay? So, first point says solve the structure by means of the two standard coefficients at the back of the page. What are these two standard coefficients? One is this. Standard beam, which means a beam with length L and bending stiffness EJ, simply supported, so hinge and roller, with a moment of unit value applied at one end. Under these conditions, the two rotations are given. The rotation at the first end, which is L divided by 3 EJ, and the rotation at the second end, which is L divided by 6 EJ. Note that when you look at this structural scheme, you shouldn't look at it as moment at the left and rotation at the left and rotation at the right. You should instead look at it by considering this is the rotation where the moment is applied, and this is the rotation where the moment is not applied. So loaded end, unloaded end. This is just to mention the fact that left and right do not play a role. What plays a role is where the moment is. Okay? Basically, and this is a question I get a lot during the written exams, you can use this coefficient also if the moment is applied at the other end. Okay? Just to make things clear. The second standard coefficient which was provided is the simply supported beam with length L, bending stiffness EJ under a distributed load of value small p. The formation is like this, it is symmetric, so same rotation at the left and the right, and the value of this rotation is PL to the power of 3 divided by 24 EJ. Basically, you have to solve the structure, you have to perform the structural analysis by means of these two standard coefficients. Clearly, what you have to take into consideration when going into the actual structure which was assigned is the fact that here everything refers to span length L and bending stiffness EJ. In our structure, the bending stiffness varies because the first span has 4 EJ, the second is EJ, and the third is 2 EJ. Now, what does it mean to solve the structure? Basically, since it is mentioned that the structure is statically indeterminate, you have to work out a sufficient number of internal forces or reaction forces in order to make it statically determinate. So to be able to then proceed by plotting the diagrams of the internal forces simply by means of equilibrium equations. Now, as we mentioned in class, this task is easy to perform in continuous beam because basically you have to look at continuous beams like simply supported beams or cantilevers with additional supports. In this specific case, if we remove this roller and this roller, so to give the letters A, B, C, D. If we were to remove the two rollers B and C, the structure would become statically determinate. It would be a simply supported beam. Which means that with respect to the statically determinate situation, we have two restraints in excess. Which means that to solve it, we have to determine two unknowns. So my choice is to work out what? As we usually do with continuous beams, we are transforming these half hinges, which imply a rotation continuity between the two adjacent spans, into full hinges like this, at point B and at point C. By doing this, our structure becomes a chain of simply supported beams. All of them are statically determinate. We can work out everything by means of standard coefficients and equilibrium equations. However, the way we go is to work with the force method, which implies that we only look at compatibility equations. What are the two unknowns? If continuity is guaranteed in this situation, it means there is a moment that is transmitted between the first and the second span across point B. I will call this unknown x1. Same happens here. This is called x2. And then there is a distributed load here, which we have to take into consideration when writing the compatibility equations. Okay? All this has to be done by using these two coefficients here. If you have printed out the written exam, you have them at the back of the page. You can look at them anytime you want. Now, how does the solution go? We use an approach which is based on considering the different loads acting on the structure, and by loads I mean the two unknowns and the distributed load, one at a time. Then we superimpose the effects and we write compatibility equations to reinstate the continuity which we lost by moving from this structure to this one. I will try to point out what does it mean that we have to reinstate the compatibility. So we start off by looking at the situation where x1 is equal to 1. You know, this is a conventional way to go. We are in the domain of linear elasticity, so we can study the effects of unknown x1 with a unit value, and then we simply multiply everything by x1. This is basically the principle that tells you that everything is proportional. If you have 100 kilograms and you have 1 centimeter of displacement, you apply 200 kilograms, you will have 2 centimeters of displacement. This is linearity. So what happens when x1 is applied? Here you have a unit moment. Basically, its effects will be visible only on the spans which are directly loaded, so the first and the second span. When we look at the effects, we have to look at them, since there is a unit moment applied, only by means of the first coefficient, which is here. Okay? So, in the standard case, when a unit moment is applied, the loaded end will rotate by L divided by 3J. The other end will rotate by L6 over 6EJ. In the case of the first span, we only have to remember that the bending stiffness is 4EJ, which means that how much does the loaded end rotate? L divided by 3 multiplied by 4EJ. L divided by 3 multiplied by 4EJ. And this is clearly equal to L divided by 12 EJ. I could also work out the rotation of the first end, but I don't need it, because its value is not relevant for the purpose of writing the compatibility equations. I have to re-explain how this coefficient is worked out. Basically, what I know from this coefficient, and pay attention, is that when you have a beam whose length is L with a certain bending stiffness, call it EJ, and you subject it to a unit moment, its loaded end will rotate by L divided by 3 multiplied by the bending stiffness. Do not look at this symbol here, EJ, as EJ. Look at it as the bending stiffness. In the case of this beam, we are doing the same. We are working out this rotation by doing L divided by 3 multiplied by 4EJ, which is the bending stiffness. Okay? So that's the point. And what matters in our case, this is something you can realize if you solve a lot of structures. What matters is the ratios between the stiffnesses. Okay? That's what matters most. Okay, first point. Second point, in this case, I look at both the rotations, but this beam is easy to consider. Why? Because, as a matter of fact, it so turns out that this is a standard beam exactly. Length is L, bending stiffness is EJ, so very easy. This center portion of our continuous beam is exactly in the same situation as the standard coefficient, meaning that this rotation is L over 3 EJ, and this is L over 6 EJ. Now you see clearly what I mentioned and what I anticipated. What does it imply to highlight these two bending moments here and to move from this structure to this? As you see here, there is a relative rotation between the two spans like this. I call it a kink in the beam, which cannot take place in the structure we started from because there is continuity. Okay? The fact that here we have continuity does not allow relative rotations like this to take place. By transforming the hinge from this to this, we allow these relative rotations to take place. So we will then have to write compatibility equations to make sure that these relative rotations do not happen in reality. And so we reinstate the situation from where we started. Why is the first 3 and not 6? This one because the bending stiffness here is EJ. No, here the bending stiffness is EJ. So the question is, why are these two coefficients like this? Because this beam is exactly the same as the standard coefficient. Okay? LEJ, LEJ. We have two EJ here. Okay? So, what we usually do in order to then write the system of for solving the two unknowns is to sum the two terms related to this relative rotation here, and I call it delta 1, 1. I sum these two rotations, which means I'm basically looking at the relative rotation across support B. L divided by 12 plus L divided by 3. This is basically L divided by 12 plus 4L divided by 12, which means 5L divided by 12 EJ. And delta 21, which is the rotation at the second point where an unknown is present, is simply the value of the total relative rotation between the second and the third span, so L divided by 6 EJ. Okay? I will stay here close to the solution so everybody can see it. Okay? Now, second task is x2 equal to 1. In this case, the bending moment is applied here. 1, this is L, this is EJ, this is L, this is 2 EJ. What we have is in the second span, same situation as above, but with reversed rotations. So at here we have L divided by 6 EJ, and here we have L divided by 3 EJ. Here the same we did with the first span. So the direct rotation, I mean the rotation at the loaded end, would be L divided by 3 multiplied by the bending stiffness. Bending stiffness is 2. So what we have here is L divided by 3 times 2 EJ, which is L divided by 6 EJ. The rotation at the last point, namely point D, I could work it out, but I don't need it, so I'm not going to write it in order not to confuse you. Okay? Also in this case, sum of the total relative rotation delta 1, 2 at the first point, which is point B, is L divided by 6 EJ, and what I call delta 2, 2 is equal to the sum of L divided by 3 EJ, contribution from the second span, plus L divided by 6 EJ, which is the contribution from the third span. So L divided by 3 plus L divided by 6 is simply L divided by 2. And that's it, okay? Don't focus so much on the symbols, rather on the meaning, okay? Again, the standard coefficients are there just to give you an indication, for example, as regards the rotation. Span divided by 3 or divided by 6 multiplied by the bending stiffness. Then the bending stiffness, for example, in this case, can vary from one span to the other. What happens with the distributed load? In the case of the distributed load, basically everything takes place only on the span where the distributed load is applied, which means looking at the standard coefficient, which is this one, we know that a beam subjected to a distributed load has a rotation which is the distributed load multiplied by the span, the length of the span to the power of 3 divided by 24 multiplied by its bending stiffness. Okay? That's the meaning of this equation. First end and second end, because the deformation is symmetric. Now, in our case, this basically means that you have a deformed shape like this, with rotations at both ends, which are exactly the same as concerns the expression as the ones of the standard coefficient. PL divided by 24, PL to the power of 3 divided by 24 EJ, first end and second end. In this case, I cannot say loaded and unloaded because the whole beam is, the whole span is loaded. Now, up to this point, it is important to focus your attention on something. If we solve continuous beams like this, which means our unknowns are the moments over the supports, if you look what I did so far, basically, under the different load conditions, x1, x2, and distributed load, only the spans which are directly loaded deform. The others do not. Look here. The moment is placed between the second and the third span. The second and the third span deform. The first span does not. In this case, there are 3 spans. Only the central one is loaded. Only the central one deforms. The other do not. This is important. Do not get confused. Do not think that if you place the load here, the other 2 spans will deform. This does not take place. If you solve this portion of the structure and this portion of the structure as regards the action forces, bending moment, and shear, you will realize that they are unloaded, which means no bending moment, no shear. Same takes place here. As a matter of fact, this way of solving continuous beams is exactly meant to make things simpler. In this way, everything is limited to the portion of the structure where the load is applied, be it an unknown or an external load. Okay, so since this is the relative rotation at point B, we will call this delta 1, 0, and this is the relative rotation at the second point, point B, and we call it delta 2, 0. Now, time to write the compatibility equation. So, to reinstate the compatibility we lost when we highlighted the 2 unknowns. Compatibility means, in our case, the continuity over support B and support C. Okay? In other words, we allowed so far relative rotations to take place. Now we want to make these relative rotations 0. We do not want kinks between adjacent spans. That's the essence of continuous beams. What is the relative rotation caused by x1 equal to 1 at support B? What is the relative rotation between the first and second span here at point B caused by x1? It consists of L divided by 12 EJ, L divided by 3 EJ, and I sum them up to make this coefficient, which is 5L divided by 12 EJ. So, we're looking at support B. There is a first contribution to the relative rotation, which is x1 times 5L divided by 12 EJ, plus what is the relative rotation caused at point B by moment x2? You can see it here. It's just the rotation to the right. It's L divided by 6 EJ. So I'm going to write here x2 multiplied by L over 6 EJ. plus what is the relative rotation at point B caused by the distributed load? Again, only on the center span, PL to the power of 3 divided by 24 EJ. Equal 0, because in reality, the original structure does not have a relative rotation between span 1 and span 2 possible. Okay? Basically, what we're writing here with this compatibility equation is the fact that there can be no relative rotations over support B. What happens at support C? What is the relative rotation caused at support C by moment x1? You can see it here. L divided by 6 EJ. So what I'm writing here is x1 times L over 6 EJ. And the fact that the coefficient in the second equation relative to x1 is the same as the coefficient in the first equation relative to x2 is good. This always happens when you apply the force method. Okay? The mutual coefficients, as we say, must be the same. Plus x2, what is the relative rotation caused at point C by x2? Here you have it, L divided by 3 EJ plus L divided by 6 EJ, left and right. Sum is L divided by 2 EJ, that's what I'm going to put between brackets to make up the second coefficient. Plus the term relative to PL to the distributed load is the same as in the previous case. I'm simply writing PL to the power of 3 divided by 24 EJ equal 0. Now let me point something as regards the signs, okay? B and C are the 2 points where we have x1 and x2. So it's the second roller and the third roller. This is B and this is C. In the first drawing, I marked them. Okay. Let me point out something as regards the signs. Very important. You may be confused at the fact that both these terms, for example, are positive, even though this rotation is clockwise and this is counterclockwise. Now, when you look at relative rotations, you have to look at them with regards to the bending moments, which we assume, x1 and x2. For example, x1 is like this, x2 is like this. So they are positive, the rotations, if they have the same sign as the moment, here and here. For example, here, moment x1 is clockwise. This rotation is clockwise. It means it's positive. Here, x2 is counterclockwise. This rotation is counterclockwise. That is why this is positive also. Okay? It's always a matter of relative rotation towards absolute rotation. When you have absolute rotations, there's no way. You have to specify either clockwise or counterclockwise. In the case of relative rotations, when we solve with the force method, you have to look at the signs in relation to the unknown bending moments you use to solve the structure. Okay? Nothing new. That's basically what we did throughout the whole course, but it's important to point out the facts. Because then later we have to solve a point which deals with an absolute rotation. Okay, this is the system that allows us to solve. I know you are all very fond of substitution. I don't like it. Makes things complicated. I prefer to work another way around, which is the one I'm going to show you. Of course, I could solve it by means of my calculator. If you have the calculator available, there are calculators which allow you to solve systems of equations. You have to, of course, do some trial and error first in order to get things right. But we can also solve it by means of another way. What is this way? In a system of equations, you can replace whatever equation by means of a linear combination of the equations you start from. Which means, if I, for example, replace either the first equation or the second equation by means of a combination of the two equations, I get the same result. In my specific case, I want a simpler equation. I do not want to have two equations with all the terms x1 and x2 in them. So I'm trying to work out a way in order to get rid of one of the two unknowns. This can be done by, if I call this equation A and I call this equation B, for example, I realize that this coefficient here, L divided by 2EJ, is 3 times this coefficient. So the idea is I'm going to look at the new equation, which is not A, it is not B, it is B minus 3 times A. Okay? Look at what I'm doing. So I'm writing here x1, then I take B, L divided by 6EJ is the coefficient, minus 3 times the coefficient coming from equation A. So here I have 5L divided by 12EJ. I'm going to subtract 3 times 5L divided by 12EJ. Plus, what happens at the coefficient of x2 if I subtract from L divided by 2EJ three times L divided by 6EJ? It basically cancels out, because 3 times L divided by 6EJ is exactly equal to L divided by 2EJ.
Posso prendere il sintoma di disturbo? Se non è un problema.
Sto registrando, comparirai nel video. No, comparirai nel video. No, passa.
Posso?
Aspetta.
No, mi scusi, non avevo capito, non volevo dire.
Basically, you see what happens here. The term with the unknown x2 disappears. Then we have here the same. We should make b minus 3a, so it's pl to the power of 3 divided by 24 minus 3 times pl to the power of 3 divided by 24. I will directly put the result because I don't have space. The result is minus PL to the power of 3 divided by 12EJ equal 0. This leaves us with an equation which is only including x1. So we can promptly and directly solve for x1 here. I will, however, have to move further away because I need space. Okay? So I will exploit this blackboard here, and then we'll move back to the initial blackboard. So I'm going to rewrite my equation. Here is x1, and here I have 1 over 6 minus 15 over 12. If you do the math carefully, I do it with my calculator. It's 1 over 6 minus 15 over 12, or let me say, it's like 2 over 12 minus 15 over 12. What is it? Minus 13 over 12 EJ. Minus PL3 divided by 12 EJ equal 0. Now, a little bit of simplifications. EJ and EJ cancel out. L cancels out with one L here, which becomes L to the power of 2. 12 and 12 cancel out. Final result is x1 equal to minus PL to the power of 2 divided by 13. Okay? Simple. Is this value nice? I don't know. It's quite simple, so not bad. Then, once we have x1 known, we can proceed with working out x2 by means of substitution. In this case, it makes sense. So let's look, for example, at the second equation which I called B. We could use it in order to get x2. What is x2? x2 L2EJ is equal to minus PL to the power of 324 EJ minus x1 multiplied by L over 6 EJ. You do the math. I'm going through this quickly. You know how to do it. Minus 1 divided by 24 plus and the result is x2 is equal to minus 3 over 52 PL squared. Note please the dimensions. We start from rotations, and rotations are L to the power of 3 divided by the bending stiffness. We get to bending moments whose dimensions are PL squared. First point is solved. Solve the structure by means of the two standard coefficients at the back of the page. This is done. What can change between one written exam and the other? Well, structure changes. Also, the set of coefficients may change. Your ability is to solve a given structure by means of the coefficients you have available, clearly. But no way you have to learn the coefficients by heart. You just have to know the procedure, not learning, knowing how to do it. Okay? Now, we have to work out the reaction forces. But before we work out the reaction forces, it is wise to solve the beams in order to see what the internal forces are, because then the internal forces allow us also to get the reaction forces. Okay? So these are the two unknown values of the bending moment, x1, x2, minus 1 over 13, minus 3 over 52. Okay? So, first span, which is AB, how is it loaded? It is simply loaded by a bending moment at the second end, whose value is x1. Now we assumed x1 to put the bottom side in tension. We got a negative value, which means that on span AB, moment x1 looks like this. So PL squared divided by 13, this is what I get. Okay? And tension is at the top, as it is usually the case when you have continuous beams over the supports. Then you have a span BC, central span. At the first end, you have moment x1, PL squared divided by 13, and this is, of course, point B. This is point C with a bending moment that is x2. Again, we assumed it to put tension at the bottom. The result is negative, which means tension will be at the top. And this value here is 3 over 52 PL squared. Then, of course, we have the distributed load, which I'm going to represent by its resultant force. I will simply lightly dash the distributed load to remember that this is not a concentrated load, this is a distributed load that comes, this is the resultant force which comes from a distributed load, okay? And then the third span, C and D, simply moment at the first end 3/52 PL squared. What do we have to work out? Let's start with the end forces, which are shear forces. I will not look at the actual force. Why? Because, as it is usually the case, if you look at the situation of our beam, we have basically no horizontal loads applied, just one horizontal restraint, which means the horizontal reaction force will be 0. Okay? So let's start with the first end. Using my convention, I will say that this is called VAB, which means the shear force on span AB at point A. Here, the shear force I will call VBA. Okay? That's my way of indicating the shear forces. I don't know if you like it. You can change it. I don't care. Important thing is results make sense. Okay? Now, how to work out VAB? Most easy way is to look at the rotation equilibrium of span AB at point B. So, to say M with respect to B of AB is equal to 0. What do we have? We have a clockwise bending moment, which is PL squared divided by 13, plus the contribution of VAB, which is again clockwise. Clockwise, yes. Okay? So it's VAB times L equal 0. What does this equation yield? This equation yields VAB equal to minus PL divided by 13. What does the minus sign mean? What does it mean? It means that the sign I assumed for the force VAB is wrong. So I assumed force VAB to be pointed upwards, to be directed upwards, means it's downwards. So I will simply do this correction. Look at here, VAB pointing upwards. Now that I know the value, I don't need the symbol anymore, and I can reverse the arrow. To save some time, let's go with VBA. What equation is useful to work out VBA? I would say the resultant force in the vertical direction of span AB equal 0. You have this force pointing downwards, which is PL divided by 13. I'm not calling it VAB anymore. We now know it's PL divided by 13, pointing downwards, minus this force here, VBA, which is pointing upwards. So VBA equal 0. No other loads applied because the span is unloaded. There are no distributed loads, no concentrated loads applied at the window. So this equation immediately gives us VBA equal to PL13. Now, look at these two equations here. Obvious conclusion, if you have a span which is loaded only by a moment and by two forces at the ends, and you assume them both upwards, there is no way. One will be downwards, the other will be upwards. They will both make equilibrium to each other. In our case, what we can do is to replace this symbol VBA by PL divided by 13. And now you look at span AB, you realize that it's in equilibrium. Why? Because this force is opposite to this force, so vertical equilibrium is guaranteed. And the moment created by the two forces who are PL13 in value and whose lever arm is L is equilibrated by the bending moment applied. Okay? Got it? Very nice. Let me change the graph. Okay, I will now delete these two equations because I need more space. Now we move to span BC. Again, VBC, and this is VCB. Okay? Two shear forces at the ends, both pointed upwards. First equation I'm going to write to work out VBC is M at point C of BC equal to 0. Okay? So the first contribution is VBC times its lever arm, which is L. This is clockwise. What else is clockwise? The moment at the second end, 3/52. You see it? It's clockwise. We are working out the equilibrium with respect to this point. The force here rotates clockwise. This moment here is clockwise, whatever point I consider, okay? So this is clockwise, this is clockwise. The two sum up in the equations, plus 3/52 PL squared. Then we have two more contributions. One is the moment at the first end. It is counterclockwise, and it's PL squared over 13. So minus PL squared over 13. And then we have the contribution of the distributed load, whose resultant is PL. It's placed at midspan, so minus PL squared divided by 2. This should be equal to 0. Quick calculation just to check my results, which I already have. 3/52 minus 1/13 minus 1/2. Result will be VBC equal to 27/52 PL. As you see, slightly above 1/2. That's the effect of having bending moments at the ends. They create an unbalance between the two shear forces. If there were no bending moments at the two ends, the load would go, as we saw yesterday, 1/2 on one side, 1/2 on the other side. In this case, as you see, 27/52 is slightly more than half of the load. Slightly more. If there is slightly more load than half of the load at the first end, then we should have at the second end slightly less than half of the load. How do we work it out? Ry equal to 0 with reference to BC basically tells us that VBC, which is upwards, 27/52 PL, plus VCB pointing upwards at the second end minus PL, who is the resultant force of the distributed load, should be equal to 0. You do the math, and what do you get? VCB equal to 25 over 52 PL. As you see, slightly less than half of the load, which would be 26 over 52. Now, at this point in time, during the written exam, you may be not sure about your result. One thing I can tell you for sure is this. Even though the beam is continuous, even though there are adjacent spans to the center one, if you have a span which is loaded like this by a load PL, then the sum of this plus this has to be equal to PL. If this is not, you're basically not guaranteeing equilibrium, the vertical equilibrium. Okay? Just to give you an idea, if you obtain in a wrong way VBC equal to 0 and VCB equal to PL, the result is wrong, but it allows you to have equilibrium. If you have VBC equal to 2PL and VCB equal to 3PL, no equilibrium, result is very wrong. Okay? I'm telling you this because it usually happens that during the written exams, you get the moments wrong. Okay? You get here a wrong value and the second and the wrong value. Okay, this can happen. Means you made a mistake in the compatibility equations. But then, if on the basis of wrong values, you still get consistent results, which means you don't get 27 over 52, you get, I don't know, 29 over 52, and the other one is 23 over 52, the result is consistent with a previous mistake. It sometimes happens that mistakes superimpose to each other. So first you get the bending moments wrong, then you get the equilibrium wrong. Okay? There are different types of errors which may overlap during the written exam. So, having said this, I will now replace here VBC with 27 over 52 PL, and at the second end, this VCB with 25 over 52 PL. Last is span CD. Just to save some time, I will spare you the details of the calculation, which can be done exactly in the same way as for span AB. Situation is the same. Span is not loaded. There is just a moment at one end. The obvious result we should get is a couple of forces at the ends which are in equilibrium with each other and whose moment is opposite to this one. So, putting this all together, you need an upward force at the first end, a downward force at the second end, with values which are 3 over 52 PL and 3 over 52 PL. Okay? And these are the free body diagrams of the three spans. These diagrams here basically allow us to do everything which follows. First of all, the reaction forces. We look at this point in the perspective of the beam. Now let's look at this point in the perspective of the support, which means here I plotted the beam just slightly after the support. Here I simply plot the support, okay? A hinge which has two reaction forces, which are HA and VA. Small portion of the beam, principle of action and reaction. The force here on the beam acts downwards. which means on the support it will act upwards, PL divided by 13, which means that if this VA is indicated like this, upwards, it will be minus PL divided by 13. So, this is to say, reaction force at the first end is downwards. PL equal to 13, okay? Here I wrote it like this. It's an alternative way. You leave the arrow upwards, but you specify that the sign is negative. This clearly makes me understand that you know it's downwards. HA, as I mentioned previously, it's equal to 0. Let's go to point B. With a vertical reaction called VB. What we have? Can you please re-explain how to see if the values are right? Is a question from the audience. Yeah, I just mentioned that in this pen, whatever the bending moments you obtain are, so in this case I got this and this value. One basic requirement is that if you have a load applied like this, whose value is PL, the two forces at the end should have a sum which is equal to PL. Okay? No matter what the bending moments are, the ratios between the two forces can change. In this case, we have a ratio between the two forces which is 4/3, but the sum of the two should be equal to the load applied, be it distributed or concentrated. Point B, we have PL divided by 13, who's acting upwards on the beam, which means downwards on the support. 27/52 coming from the right, it acts upwards on the beam, which means downwards on the support. The reaction force VB is therefore the sum of the two forces, 1/13 plus 27/52. The value is 31/52. And by this you see that at inner supports, the reaction force is not equal to the shear forces of the beams. Okay? In other words, also the shear forces on the beams are not equal to the reaction force. Okay? Very important for the purpose of design. Let us look at point C. Same downward force, 25/52 coming from the left, 3/52 coming from the right, both downwards. So BC is equal to what? 25 plus 3, 28/52 PL. If you want, you can also make it simpler. It becomes, you can divide it by 4, so it will be 7/13. And then point D. Minus 3/52, as in the situation of point A. So, the shear force on the beam is downwards, which means it is reversed on the support, which means if I assume the reaction force is upwards, it will have a negative sign, which is downwards. Okay? Now we have to plot the diagrams of the internal forces. It's better to use this blackboard. Okay, first diagram is the shear force diagram. Shear force diagram, as we did yesterday, positive if clockwise, first span, second span, look here at the beam, AB. At the first end, how is the shear force? Downwards. Here at the first end of my sign conventions, it's upwards. So this means that all along AB, shear force is negative. So I will put here a rectangle with a minus and PL over 13. That's the value. Who again, I didn't say as I did yesterday, here no forces applied, I should expect a constant shear force. Here, distributed load applied, I should expect a linear diagram of the shear force. First end, the value of the shear force or the shear force is upwards, which means it's positive, and the value is 27 over 52. How much is it in relation to this one? Much more. This is 4 over 52. So 27 over 52 will be 5 times more. This means I cannot draw the diagram in scale. I can plot here a note, or I can simply remember it. This is 27 over 52 PL. At the second span, at the second end, we have 25 over 52. Slightly less than that one. Okay? It points upwards, whereas my sign conventions at the second end assume the shear to be positive if it's downwards, which means the 25 over 52 at the second end is negative. So plotted on the other side. How is the shear force? In this beam, I said linear, so I simply draw a line connecting the two. This portion is positive, this portion is negative. Last span is CD. Shear force at the first end is upwards, as in my sign conventions where the shear force at the first end is upwards, which means here we have 3 over 52, constant over the whole beam and positive, 3 over 52 PL. What does this discontinuity represent? The distance between these 2 points here. What does this jump represent? It represents a concentrated force, namely the reaction force at point B, VB, 31 over 52. Same here, there is a jump, and the jump is exactly equal to the reaction force at point C. Reaction forces are no different from concentrated loads. As a matter of fact, they are concentrated loads. So their effect is the same as we saw yesterday when you have a concentrated force in the middle of the beam. Okay? Jump in the shear force. Notably, and this is something we have to bear in mind, there is a 0 point of the shear force at what distance from the first end? 27 over 52 L. Why do we need to look at this point of 0 shear force? Because we know where the shear force is 0, the bending moment is going to attain a maximum value. Okay, I will now erase the blackboard because I need more space to plot the bending moment diagram. M, I plot it on the tension side. First span, second span, third span. What values do we know already? The moments over support B and C, both negative in the sense that the tension is at the top. Here we have 1 over 13, so this value is PL squared over 13. The ratio between the two moments, I said, is 4 over 3, so this will be 3 over 52 PL. What happens in the first and in the last span? We know no distributed load applied, no concentrated load applied, bending moment should be linear. So since we know that at the first end A and at the last end C, where there are rollers, the moment is 0, this is the bending moment diagram on the first span. This is the bending moment diagram on the third span. Linear. Okay. Now we have to work out the maximum bending moment because in the center span where there is a distributed load, the bending moment diagram is parabolic. So we need a third point to plot. We will work out the value of the maximum bending moment. So we have to basically look at the bending moment where the zero shear force is. So like this. We look at a portion of span BC, which is 27 over 52L. We know that at the first end we have 27 over 52 PL and a moment which is PL squared over 13. We know that we have a distributed load. And we know that here we have the moment M maximum. So we have to write equations for working out M maximum, okay? Most convenient equation in this case, since we know that there is a zero shear force here, is to write the equilibrium with respect to this point. So I'm basically writing moment with respect to B of half, almost half. Let me write portion of BC equals 0. So what I have is PL squared over 13, which is counterclockwise, plus maximum bending moment M max, minus the contribution of the distributed load, which is 27 over 52 PL times 27 over 52 L multiplied by 1 over 2 equal 0. This term, which may seem complicated, is simply the fact that here you have a portion which is 27 over 52, so the load is 27 over 52 PL, and the lever arm is the same length, 27 over 52, divided by 2. By solving this value, what you get is, let me check it, You don't need to do it in fraction. You can also do it in other ways. I will write you with fractions and then the value in decimal points. So fraction is 313 divided by 5408 PL square, which is equal to what? 0.0579. 0.0579 PL square. Okay? How is this in relation to the first bending moment at the first point? It's slightly smaller, so this point will have something like this and like this. Okay? Here the value which you have is maximum bending moment. Now we know that with the bending moment, we are able to give a qualitative indication as regards the deformed shape. It was not requested in the assignment, but it is useful for what comes next in order to understand whether my result is right or wrong. So this is the undeformed shape. On the basis of the bending moment, we know how the deformed shape will look like, more or less. We know that we have a curvature which is like this, where the bending moment is negative. So again, where the bending moment is negative, curvature looks like this. Where the bending moment is positive, curvature looks like this. When the bending moment is negative, curvature looks like this. Deformed shape should pass through the points of the supports, and there will be contraflexure points where the bending moment is 0. Putting this all together and remembering that this span here, the center span, is loaded, we have something which looks like this. Okay? Remember, not needed, but it allows you to understand whether you get something right. Because now I have to move to the last point of the first part, and then we can finally take a break. Okay? So, the fourth point of the first part was dealing with the rotation at point B. When I say rotation at point B, there is no possible doubt that I'm talking about a relative rotation, because in the actual structure there is no relative rotation, there is continuity. So when I'm asking the rotation, I'm meaning the absolute rotation. Now from my qualitative sketch of the deformed shape, I can already assume what the rotation will be. Clockwise or counterclockwise at point B? Clockwise. Let's see if we get it from the calculations. How can you calculate the rotation at point B? We've seen it previously. Rotation at point B can be calculated either to the left of point B or to the right. They are equal. That's exactly what we imposed when we wrote the compatibility equation. Writing that the relative rotation is 0 implicitly means writing that the rotation to the left is equal to the rotation to the right. What is the simplest rotation of point B we have? I didn't delete what I have there because it allows me to show you. Here, as you see, there is this rotation at point B. In all the other situations, which means x2 equal to 1, P applied, there is no rotation to the left of point B. You agree? You check it in your notes. If we look at the rotation to the left of point B, this is the only case where it takes place. Okay? So, I can calculate the rotation to the left of point B to the left of B, assuming it to be clockwise. How? Again, bending moment x1 with a unit value causes a counterclockwise rotation whose value is L over 12. Agree? If I want the actual rotation, I should A, replace the unit value with the actual value of x1, and if I want the clockwise rotation, I have to put a minus sign. So I'm going to write it as minus x1 times L over 12EJ. Again, the rotation to the left of B, which is equal to the rotation to the right, so I can calculate either the one or the other. If the bending moment x1 has a value of 1, is counterclockwise and equal to L divided by 12EJ. If I want the rotation to the left of B clockwise, I put the minus sign and I replace the unit value 1 with the actual value of x1. In writing, minus, what is the value of x1? P minus PL squared divided by 13 times L over 12 EJ equal to minus and minus cancel out. It yields a plus. We have PL to the power of 3 on the top of the fraction sign. The bottom we have 13 times 12. How much is it? 110 times 10 is 100, 30, 20, 150, 156 EJ. Agree? Check it. Value is positive, which means our rotation is clockwise, as we should have expected from the qualitative sketch of the deformed shape. Got it? And now, time for a well-deserved break for all of us. So, point E reads, design the longitudinal reinforcement at the top of the section at the point of minimum, between brackets, negative, bending moment of span AB, assuming 14 millimeter diameter rebars. Okay? Basically, we have to design the longitudinal reinforcement at the top of the section. As a matter of fact, why at the top of the section? Because, as you see here, the bending moment is such that the tension is at the top of the section. So, value of the bending moment is PL squared divided by 13. So, this was point E of the assignment. So, moment applied, I will call it like this. Applied is PL squared divided by 13. Now, with the numbers, L is 5 meters and P is 35 kilonewton over meter, which means this value is 35 kilonewton over meter times 5 to the power of 2 divided by 13. the value in numbers is 67.37 kilonewton meter. 2 digits after the comma are enough. Okay? Section is like this. Rectangular, the dimensions were provided. B, which we don't need, but I will give it anyway, is 15 centimeters. The reinforcement should be placed at the top. So I'm going to mark it like this, AS. The effective depth, which means the distance from the top reinforcement to the bottom, is D prime 30 centimeters. Now, in this case, since you have to design the reinforcement, you cannot calculate the neutral axis depth in detail. You don't have the data. Okay? You have to adopt the well-known approximation that tells you that in a section subjected to bending moment, how is the bending moment resisted? In our case, it's like this, negative. I called it M applied. It is resisted by a tension force in the reinforcement, T, and a compression force in the concrete, where there is a portion which resists to the stresses. The internal lever arm, which we call Z, can be approximated as 0.9, the value of the effective depth D prime. So in our case, this will be 27 centimeters. Okay? If this approximation holds, then T is simply equal to the moment applied divided by the internal lever arm. Careful with the units of measure. If we want something in kilonewtons, a force in kilonewtons, then we will have to rearrange this bending moment in kilonewtons times centimeters, or transform the centimeters into meters. So I will do the latter, 767 divided by 31 divided by 0.27. This yields a tension force which is equal to 249.28. I will round it to 249 kilonewtons. Now, another datum which was provided in the written exam was the design yield strength of the steel, which is FYD equal to 350 megapascals. So we know we have to resist this tension force with the reinforcement with a steel whose yield strength is 350 megapascals. This means that the minimum area we need at this section, AS minimum, should be equal to T divided by FYD. To get the dimensions right, you have to transform the kilonewtons into newtons, because we know megapascals are newtons over square millimeters. So 249 to the power multiplied by 10 to the power of 3 divided by 350. This is equal to what? 711 square millimeters. Okay? If I was in a hurry, I could consider my design task done. It is not. because I have to transform this into a number of commercial rebars. As a matter of fact, the assignment said design the longitudinal reinforcement, blah, 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 assuming 14 millimeter diameter rebars. So my final answer should be how many 14 millimeter diameter rebars I need. So what I'm going to do is work out the number of rebars by dividing AS minimum by P times 14 to the power of 2 divided by 4, which is basically the area of one 50 millimeter rebar. Okay? I'm going to do that for you. You can check it. The result is 4.62. What is the final answer? If I get 4.62, since I cannot have a decimal number of rebars, I only need integer numbers. 5. This is how we indicate 5 14 millimeter rebars. The symbol phi stands for diameter 14. Okay? What does the section look like? In the end, section B will be something like this. 1, 2, 3, 4, 5. Then we need 2 at the bottom to keep the stirrups in place. This is what the section looks like. Okay? You take some time to write it down, and I will then erase everything and go to point F of the written exam. Okay? Point F reads, check, not design, check. The longitudinal reinforcement at the point with maximum, between brackets, positive bending moment of span AB, assuming it consists of 3 16 millimeter rebars. And in this case, since it is a check problem, design aids were provided at the back of the page. Okay? What are these design aids? Basically, I will replot them here. It gives you the expression of the neutral axis depth in a rectangular beam. So in a rectangular beam subjected to positive bending moment, we have compression at the top, reinforcement at the bottom. This leads to a distribution of stresses which looks like this. In the concrete at the top, maximum values FCD, design compressive strength of the concrete, and FYD at the bottom. Now the neutral axis depth, which is this, x, is given by the following expression. FYD AS times divided by 0.8 FCD times B, like this. I should mention that in the written assignment which I sent out, there was a typo in point F. Moment of span should not be AB but BC. Okay? If this is the neutral axis depth, the internal lever arm in this case is V minus 0.4x. These equations were explained in class. I will not go through the whole theory again. Just be aware of the fact that in this case, if the portion in compression is x with a variable distribution of compressive stresses, it can be approximated by assuming that this portion is 0.8x. And from this, you get this expression and this expression. Why couldn't you apply this one for the previous point? Because as you see, the neutral axis depth depends on the reinforcement amount. If we don't know how much steel there is, we cannot use this expression. So it can be used when you have to check a section, cannot be used for design because this value here is unknown. That's why I used the approximated expression for the internal lever arm, namely 0.9 d prime. Okay, what is the moment applied where the bending moment is maximum? It's this one, maximum, with the value I provided earlier. The final numeric value is 50.64. So the moment applied at this section is 50.64 kilonewton meters. Okay, B we know already. B is 15 centimeters. FYD I gave previously. FCD, this was another datum provided, it's 15 megapascals. So first thing you do is to work out the neutral axis depth. Now, FYD 350 times AS. How much reinforcement is there at this section? Again, point F, 3 16mm rebars. So here it's 3 times P times 16 to the power of 2 divided by 4. This is the amount of reinforcement. Divided by 0.8 FCD, compressive strength of the concrete, 15, multiplied by B, the width of the beam, 15 centimeters, but we are going to transform it into millimeters in order to be consistent with all the other quantities. 150. This yields a neutral axis depth. I will calculate it for you. You can do the calculations with me. (117 millimeters). 117 millimeters. Internal lever arm is D minus 0.4x. In our case, in the case of the positive bending section, this was 30 centimeters. Maybe different from the other section, D prime at the top may be different from D at the bottom, but in our case it was the same, 30. So here we have 300 minus 0.4 times 117. This is equal to 253 millimeters. Let's just give it a check. How much is 253 in relation to 30 centimeters? So how much is 253 over 300? (0.84D). This is just to show you why we assume usually in the design phase 09, because usually for ordinary reinforced concrete sections, as you see, even with an accurate calculation, you end up with a value which is close to 09. Fair approximation in the design phase. If this is X and this is the internal lever arm, what will the resisting bending moment of this section be? Which means the maximum value, the section, maximum value of bending moment it can sustain. Resisting bending moment, MRD, is equal to FYD times AS, which is the maximum tension force in the reinforcement, multiplied by Z. With our numbers, 350 multiplied by the reinforcement, 3P times 16 to the power of 2 divided by 4, multiplied by 253. What is the result? Again, 350 times 3 times P divided by 4 times 16 to the power of 2 times 253 divided by 1 million to go back to kilonewton times meter. 53.41. Is the section okay or not? The assignment said, check the section. What is your answer to the check? Okay or not okay? This is the maximum value the section can sustain. This is the value of the bending moment applied. Since this one, resisting bending moment, is larger than the moment applied, section is okay. Okay? No questions from the audience online? Questions from the audience live here? No. Last but not least, we have to do point G, which reads, design the spacing of the stirrups required at the right of support B, assuming the stirrups consist of two-legged vertical 8 mm diameter rebars. Lots of things. We will now split it into different concepts. First of all, important thing, the assignment clearly says that you have to design the stirrups to the right of support B. Why? Because, as we mentioned earlier, and you can see it here, the shear force changes across support B. To the left has a value which is PL divided by 13, and it's negative. To the right, it is 27 over 52, and it's positive. Now, as regards the sign, we don't care about the sign if we use stirrups, but the value is important. Because if it says to the right, it means you have to take this value and not this one. It would be very wrong also to take the reaction force at point B as a shear force. As a matter of fact, earlier this morning I pointed out that there is a difference, a big difference between the reaction force, which is the sum of the two shear forces, and the shear forces on the two spans converging into support B. Finally, this is the value we have to take. 27 over 52 PL. So our V applied is 27 over 52 PL, which means 27 over 52 times P, 35 times 5. These are the values of the distributed load and of the length L. Value is 90.86. kilonewtons. Now we know that by means of the traditional truss model, the resisting shear force in a section at a given location is provided by the following equation. Internal lever arm Z times FYD, design yield strength of the steel for the stirrups, multiplied by ASW divided by S, which is the spacing. Now, Z is the internal lever arm, FYD is the design yield strength, ASW, if we have two-legged stirrups, which means stirrups that run like this along our section, ASW is the sum of these two legs of the stirrups. So I could write it as number of legs multiplied by P phi S to the power of 2 divided by 4. So the area of the stirrup multiplied by the number of legs. This is very important. It's crucial to the concept of resisting mechanism. The spacing is the distance between one stirrup and the adjacent one along the span of the beam. You know, the closer the stirrups, the higher the shear. The further away the stirrups, the lower is the shear the beam can sustain. Okay? So I typically expect in the supports area where the shear is higher to have more closely spaced stirrups other than what happens, for example, at mid-span. Okay? Bear in mind this, the closer the stirrups, which means the lower the spacing, the higher shear force the beam can sustain. Now, what is our design equation? Our design equation is based on the shear applied. We determine the spacing needed. So, in this case, S maximum, not minimum, and I will elaborate further on this, is internal lever arm times FYD times ASW divided by the shear force applied. What is internal lever arm? We have no information at the point where we calculate the shear, so to the right of support B. I mean, we could assume to use the previous reinforcement and to calculate Z in an accurate way doesn't make sense. We use the approximate formula, which is 0.9 times 30 centimeters, which becomes 300 millimeters. Again, work in millimeters and newtons. Then design yield strength, it could be different between longitudinal reinforcement and stirrups. It is not in our case, so 350 is okay. Then ASW, the assignment clearly said or clearly read vertical 8 millimeter diameter rebars with two legs. So this is 2 times P times 8 to the power of 2 divided by 4. Again, P times 8 to the power of 2 divided by 4 is the area of one leg. I put the 2 because there are two legs connecting the top and the bottom. Divided by shear force is 90.86 kilonewtons, so 90860 in newtons. And I do the calculation. The calculation is very easy. Result is 104 millimeters. How do we round it up or down when you place stirrups? you round it to the next centimeter, or better. Would be nice to have multiples of 5. So in our case, there are two choices. Either I go up to 15 centimeters or I go down to 10 centimeters. As I said previously, the lower is the spacing, the higher is the shear force which can resist it. So in this case, 10.4 becomes 10. That's why I wrote here, this is the maximum stirrup spacing. This becomes 10. So I will write S provided equal to 10 centimeters. And the people who place the stirrups are happy because 10 centimeters is a very nice number instead of 10.4. Okay? So that's basically it. If you have some questions you'd like to share also with the people online, if you people online have a question, which I can answer at the end of this assignment. I know it took me very long for the first part, but my experience tells me that my students usually struggle a little bit more with the structural analysis part. That's why I focus so much on equilibrium, internal forces diagrams, and all the other things. So if nothing else, I will close the recording and wrap it up.